All right, we're back. We're on page 9 of notes 4 of Calc C, and we're just going to decide, do these series converge? Definitely. Do they diverge? Definitely. Or do we not know what we're doing yet? Which is certainly possible because we know a very limited amount about series. So let's see what we can do. So first one, n factorial over 2 to the n. Let's look at the limit. So the limit as n approaches infinity of n factorial over 2 to the n is definitely infinity. So like when you're trying to work that out, like, so some people can't work that out immediately in their heads. Just think like, I don't know, 50 factorial over 2 to the 50th, right? So 50 factorial is 50, 49, 48, 47. It's a product of all those numbers. 2 to the 50th is just 2 times 2 times 2 times 2. So 50 is bigger than 2, 49 is bigger than 2, 47, 46, 45, they're all bigger than 2 until you get down to the end where it's like 2 over 2 and then 1 over 2. So the 1 over 2 loses, but everything else wins. So n factorial definitely is beating 2 to the n. So since we get infinity and we don't get 0, therefore n factorial over 2 to the n diverges. I'm going to say by nth term test. Nth term test. So the nth term test can only tell you if something diverges, and in this case it did, which is good. All right, let's try it again. So limit as n approaches infinity of n squared plus 2 over n cubed minus 6. So you can do whatever you want here. You divide through by n cubed. You could use L'Hopital's rule. You could just look at it and be like, it's quadratic over a cubic, so definitely the limit's going to be 0. This limit is definitely 0. Therefore, we can make no conclusion. The only way we could make a conclusion is if that limit had been not 0, right? If it had been 3, then we'd be like, oh, diverges because it's not 0. But if we get 0, it doesn't tell us anything because the n-term test is for divergence. It can't tell you about convergence. We don't know enough to do this problem yet. Eventually, we will find that this series actually diverges, which, like, I don't know if you would guess that, but it does. And eventually we'll know enough. This one is definitely geometric. So I'm going to say this, it's geometric. R is 3/4, which is less than 1. Therefore, we can actually find the sum. So what are we doing here? We're doing, well, all right, let's write the thing. So plug in 6 and you get 100 3/4 to the 4th over 1 minus, the ratio is 3/4. I'm not going to simplify that, but it does simplify, and it does have a finite sum. So that one's geometric, just recognize it. This one, I mean, the limit is definitely 0, right? 1 over n by itself is going to 0, and then if you raise it to the nth, it's going to 0 even faster. So this is 0, no conclusion. But if we think about it, we can kind of work out what's happening here. So just think, we don't know enough yet to really, really do this. But if we think, so let me put this in a different color. Let's think. Think. Okay, so 1 over n to the n is definitely less than or equal to 1/4 to the n for n greater than or equal to 4, which is what we need, right? Because we're going from 4 to infinity. So why am I saying that? Well, like 1/4, so if n is equal to 4, then we just get 1/4 to the n versus 1/4 to the n. Guaranteed those are equal. If n is equal to 5, we get 1/5 to the 5th versus 1/4 to the 5th. But since 1/5 is smaller than 1/4, when we raise it to the power, it'll be even smaller. So that's true. It's actually true forever. And this, oh God, this converges because it's geometric with r equal to 1/4. So if you think about it, this one must converge because it's smaller. So the terms are always positive, and it's smaller than a convergent thing. So it's like we have this one series, and then on top of it is another one that's kind of like landing right on top of it. And the one on top is converging. It's it's going to push it down. So eventually we'll know that this that we've just done here is called the direct comparison test. We didn't do it officially, but if you just think about it, it really makes sense. It's kind of like the squeeze theorem, basically. Like we squeezed this series in between just 0, which definitely converges to 0, and then 1/4 to the end, which also converges. So we kind of like forced it to happen. But anyway, we don't need that yet. The next thing we're going to talk about while we're here is the sum from 1 to infinity of 1 over n, which has a famous name. It is a famous series. It might actually be the most famous series. I don't really know. I don't have an opinion on that one. I think it's probably the most famous. The sum from 1 to infinity of 1 over n is called the harmonic series. Look it up. It's got something to do with music that I'm not well versed in. Let's see what's happening with this. So this is a really important series. And it's famous, and you're just going to memorize what happens to it. But let's see if we can work out what's happening. So I'm going to go to the calculator, and we're going to do all these partial sums. And fortunately, the calculator is just going to do them for us. All right, so we want the sum from 1 to, let's say, k of 1 over n, and then we'll just feed it k values, so such that k equals 1. And we get 1. So I guess I'm supposed to write these. 1, and then we're going to make it 2. So we're doing powers of 2 for some reason. 1.5. So that's bigger. 3 gives us 1.833. That's bigger. 4 is 2.083. It's bigger. So it's still, it keeps getting bigger. Next is 8. Oh wait, did I do 8? I don't know what's happening. 3. Oh, not 3. What am I doing? You know what I should have done is I should have done 2 to the k. I don't know. This was supposed to be 4, which was 2 points. So I'm fixing the notes even though you can't see them, because you know, for completeness. So 4 is 2.083, and then we're going to 8, which is the next power of 2. It's 2.718. Bigger. That one's almost 8. Unrelated, I believe. 16, 3.381, 32, 4.059. So, I mean, I think there's enough evidence here to say that this thing is definitely just going to diverge. It looks like it's diverging slowly, though. And, like, I don't know that you can definitely say based on this that it's diverging. Because, like, what if it's converging to, I don't know, like 10? What if it's exactly 10? Like, who knows? If you can write, so the Inspire kind of runs out of steam soon. If you, like, I'm using like Python or something on a computer, you can do a much better job with this, or get like way more, I guess. I don't really know why that's true, but it's so much faster. I guess because the computer processor is probably a lot faster. But anyway, I'm going to say I think this is definitely diverging, which I also think is a little surprising because 1 over n, I mean, like, the limit is definitely 0, right? So the nth term test, it does not tell us that it diverges. The nth term test basically says do another test. So we start looking at the partial sums. Looks like the limit of the partial sums is not going to be finite. And so I think that from 1 to infinity of 1 over n diverges, which I think is also surprising because, I don't know, 1 over n seems pretty small. Even like when n is 100, you're already pretty small. But I guess it's not going to be finite because the limit of the partial sums does not appear to be finite. So I'll be back in the next video and we will talk more about that, and I will see you there.